wave behavior is called diffraction. Diffraction is really the bending of waves around a barrier, or when the waves have to travel through a narrow opening. Waves, and you can think of it as it could be a jetty or a pier or something in the ocean. Out here we have the ocean, but we have some barrier. The waves are going to have to go through this narrow opening. When this happens, the waves actually interfere with each other. So they crash into each other. Diffraction then can cause interference. So interference is when really waves crash into each other. There's a couple types of interference. When they crash, they can either combine and become even larger waves, or they can cancel each other out. So think of it as similar to when you're on a trampoline. Woo! Jumping up and down on the trampoline. Right? Let's say there's 3 of you jumping at the same time. Jump higher. If everybody jumps at the same time, you go up higher. But if you're not jumping at the same time, you cancel each other out. You can't jump as high as you would alone. On a trampoline, say you and your friend are jumping on the trampoline. You jump at the same time. If we combine them together, it's called constructive interference. So in the end, have larger waves. Okay, so this plus this is this. So if the 2 of you are jumping on the trampoline at the same time, you're going to jump even higher than you would alone. You're really combining the 2, making larger waves. That's why you can jump high. So you're jumping together, and I'm doing this. Woo! And interference then is when waves collide with each other. This can happen during diffraction. 2 types of interference. The first type is constructive interference. And this is the example I gave on the trampoline. When 2 people jump at the same time, jump higher when the 2 of you are jumping at the same time. You have the opposite happening. So on the trampoline, if the 2 of you are jumping, but you're jumping opposite times, so when you go up, the other person's coming down. This is when the waves are not combining, they cancel each other out. Combine these 2, they cancel each other out. All right, so this is destructive interference. So when they cancel each other, you're not going to be able to jump very high. It's better if you did it alone. So on a trampoline, you're experiencing constructive interference and destructive interference. Absorption. And this is when the energy in the waves is absorbed by something. And it's converted into another form of energy, for example, heat. So you could have the light, if you think of a pavement or a blacktop, black roads. That heat, that light, a lot of that light is absorbed in the road. It gets very hot. So that is absorption. So if you think of the ocean, as you go further and further down, it gets darker and darker. Pretty soon there's no light at all. Because that light has been absorbed at the lower levels of the ocean. If you think of soundproofing your room, soundproof in the classroom, the walls, so that most of the sound waves are absorbed. A few of them are going to pass through, a few might reflect, but you want to make sure most of them are absorbed. So if they're absorbed, the sound is not going to pass through. The colors, we have a red pool ball, we have a yellow pool ball, and we have a purple pool ball. Why do we see different colors? Why are these different colors? It really has to do with the absorption or reflection of light. So if we look at this yellow pool ball, for example, this is not the real size pool ball, this is it. Why is it yellow? There's nothing in the pool ball that makes it yellow, really. There's nothing inherently in this ball to make it yellow. It's the reflection of light, which is amazing. It's hard to even think about this, but when the light waves hit the pool ball, some of them are absorbed, some are reflected. So here on the pool ball, we have light coming in. White light is made of all the different colors of light. So please review the EM spectrum, the electromagnetic spectrum. I know we drew it a couple times, but if you think of colors, they range in wavelengths. That's what makes colors different colors. Visible light, remember visible light is only a small part of the electromagnetic spectrum, because this is actually the light we can see. But there's many more wavelengths of light we can't see. So the visible light, we're going to say, just if I have the whole electromagnetic spectrum here. All right, the visible light we're going to say is right here. Let's just say this is a section of visible light. It's going to range from longer wavelengths to shorter. So remember the wavelengths, the distance from crest to crest or trough to trough. So this is the longer wavelengths. You can see these are getting shorter and shorter. Just in the visible light, right here, or white light. So the longer wavelengths are more like red, orange, yellow. So red. The shorter wavelengths are more toward the violet. So the yellow would be around here, wavelengths. So what happens is then you've got all this visible, all of the different white light, which is made of different colors. All these different colors coming in. And really they all get absorbed except for the color we see. And the color we see then, in this case, is yellow. The wavelength for yellow. So, like this. That's the one that's reflected in this pool ball. That's why we see yellow. This pool ball is purple. Why do we see purple? Because this pool ball is absorbing every other color's wavelength except for the shorter ones, the violet, purple. That's the one that's reflecting. That's why we see purple. That's how we see color. It's amazing. It's how the light that's reflected is the color we see. In the atmosphere, we have an atmosphere. We have gases in the atmosphere. We have oxygen, nitrogen. The shorter wavelengths are easier for the gases to reflect. Remember the time when we had a lot of fires? It looked like we were living on Mars. When I looked outside, it was like red. And why was the atmosphere, why was it the air, why did it look like it was red? The sky looked red. At that time, then, we had like a shift to this end of the visible light. Because the atmosphere was full of, there wasn't just these gases, we had other gases. A lot of carbon dioxide, a lot of dust actually in the air from the fires, the smoke. So what that does then, it slows down, and it takes longer to travel for this light. It takes longer for this light to travel through the sky. It's smoky. So you tend to see the longer wavelengths, red color. Because it takes longer for the light to travel through the sky when it's full of smoke. And the same thing if you think of sunset. Why is it red? Why is the sky turn orange during sunset? It's the light we're seeing. The light from the sun is not as direct. So it's has longer time to get to us. Longer time, these longer wavelengths. So we see the longer wavelengths during sunset. The sun turns, the sky looks orange. And the light has a longer distance to travel to us. And it has a longer distance to travel, just like with the smoke. It has to go through more particles. It has a longer time. You see the longer wavelengths of light. But dark colors, they absorb more of the light. So dark colors absorb more light. And when they absorb more light, that means that when it absorbs it, that means the light waves are going to be converted to other forms of energy, such as heat. And that is why, if you wear black all the time, like I like to wear a lot of black, but in the summer when it's hot, I used to live in Florida, if you wear all black, you'd get hotter than if you were wearing all white, because black, being dark, absorbs a lot more colors. And when it absorbs more colors, that means technically it's absorbing more light waves, it's absorbing more energy. And then that energy that it's absorbed is converted to a different form of energy like heat. So it gets hot. So it's hot because the darker colors absorb more light energy.